Okay, so we're talking today about work, energy, and elasticity. Now, the total work done on an object we can define as the product of the net force and displacement. And as we saw earlier, net force is ma, that's Newton's second law. And then we can put in a factor of a half and a factor of 2 and not change anything. And then the MAD have to be there. But of course, 2AD, that is VF squared minus VI squared. And then when you multiply that through, we find that the total work done, which is the product of net force and displacement, is 1/2 mvf squared minus 1/2 mvi squared. That's just the change in kinetic energy. So that's one way at looking at the relationship between work and energy. I personally don't think it's useful because then you have to find the work done by gravity. And the easiest way to find the work done by gravity is to consider potential energy. So another formulation of the work-energy theorem says that there's two different types of work. Work that just changes the form of energy, but not the total. And that's called conservative. And examples of that include gravity and springs. And in the case where you have a conservative force, the conservative force work can be found using, the work done by a conservative force can be found using a potential energy function. And it's just the potential energy difference. Now the other type of work, remember we said there's two, right? One, two, is the work done by a force that changes the total mechanical energy. Okay? And an example of a force like that would be something like friction or an applied force. And these are called non-conservative forces because they don't conserve mechanical energy. Now, in the case where you have non-conservative forces, then, the mechanical energy at the beginning and the mechanical energy at the end will be different. They'll be different because of the work done by non-conservative forces. So, this is another statement of the work-energy theorem. And in my mind, it's more useful. Now, equivalent to that, another way to look at this equation is that this just represents other forms of energy other than mechanical, and the total energy of the universe is constant. So if we go back to our previous formulation, mechanical energy plus the work by non-conservative forces equals final mechanical energy. This is just other forms of energy. It's thermal energy, it's chemical energy that are moving into or out of the system. And so these, the second and third perspective are essentially the same. One says mechanical energy of the system changes when there's non-conservative work. This one just says the total energy, all forms for the universe must be the same. Let's just quickly prove those two relationships. First, let's show that conservative work is a potential energy difference. So we want to find a work done. Well, we know a work is a force times a displacement. Let's just consider a special case where we're lifting an object, and we want to find the work done by the conservative force. That'll be the work done by gravity. So the force is mg. However, because the motion is this way, and the mg force is this way, because of that, the work done is actually negative because the force is opposite to the displacement. So we're finding the work done by gravity here. And of course the distance is h. So we find that the work done by gravity is negative mgh. That of course is 0 minus mgh. And because we're starting here, we could say that's a 0 of potential energy, and then we're ending up here. We see that the work done by gravity is a potential energy initial minus final. So that's a potential energy difference. And so this, at least, is a plausibility argument that the work done by a conservative force is given by a potential energy difference. Next, let's prove the other result, which is that mechanical energy changes when there's non-conservative work. We'll start with the result we proved previously, which was that the work done by all forces is a kinetic energy change. Well, all we're going to do is we're going to say that the work done by all forces includes the conservative ones and the non-conservative ones. And those non-conservative forces, well, that's friction and applied forces. We'll leave that like that. But we just showed that the work done by conservative forces can be found using a potential energy difference. Oh, sorry, this should be plus. And this should also be plus right there. So this is the total work done. These are the conservative forces work, and these are the non-conservative forces work. And we know that's got to equal a kinetic energy change, kinetic energy final minus kinetic energy initial. So gathering the final terms on one side and the initial terms on the other, so this one goes over here, this one goes over here, we arrive at kinetic energy plus potential energy at the beginning. This stays where it was, work by non-conservative forces, equals potential energy plus kinetic energy final. And this is, of course, what we mean by mechanical energy. It's the sum of the kinetic and potential energy. So we have proved the result. Well, let's use that result then and set up a number of work energy equations based on it. So for each diagram, we're going to write a work energy equation. So something of the form mechanical energy at the beginning plus work equals mechanical energy at the end. So mechanical energy at the beginning, that includes kinetic and potential. So is it moving? No, there's no kinetic. Oh, it does have potential energy. But notice that at the end, it's at the same height. So we can just make this our reference level, our h equals 0. And that means at the beginning, there's no potential energy and no kinetic energy. At the end, because it's moving, it's got motion energy, kinetic. Now, there was work done in the throw, and that equals the amount of kinetic energy. Now, the work done in the throw is related to a certain portion of the chemical energy. The efficiency of the muscles would be the amount of work you did in the throw over the amount of food energy that you used. And of course, some of that food energy gets converted to thermal energy, so the energy of the universe is conserved. So that's that third perspective I mentioned. In the second perspective, you do some work, and that gives the ball kinetic energy. Let's write down an equation here. So this again will be our 0 of height. So there's no potential energy. At the beginning, we can see we've got an amount of kinetic energy, relatively large. Final mechanical energy, it's slowed down, so it still has kinetic energy, but it's just a bit smaller. So I'll represent that graphically. And there was work done by friction. Now, that work done by friction will be negative, so it makes sense that we have a smaller kinetic energy at the end. In terms of the energy of the universe approach, so this is negative. That will just be a negative amount of thermal energy. So another way to write this equation would be to say that the kinetic energy you had at the beginning, some of it was still kinetic energy at the end, and the rest had been converted to thermal energy. Now, this thermal energy will be a positive value, and the work done over here is a negative value because friction opposes motion. So this is the second perspective, this is the third. Again, just to show you that they're consistent with each other. Next, let's imagine that engines do work propelling a rocket. So we'll say that at the beginning, there's no potential energy there, and obviously there's no kinetic, so no mechanical energy at the beginning. At the end, it's got height, and it's moving. So it's got both potential and kinetic energy at the end. And that work was work done by the engine, of course. So the work done by the engine changed the mechanical energy of the rocket, gave it potential and kinetic energy. In terms of the energy of the universe approach, you would say that this engine work, well, there was some chemical energy input to the engine. Some of that chemical energy was converted to useful work in making the rocket go. The rest was converted to thermal energy, and the energy of the universe is conserved. So that chemical energy equals the engine work plus the thermal energy. Let's try a couple of more work energy equations here. An escalator does work lifting passengers. They start at rest, they end at rest, so there's no kinetic. This is our zero of height down here. So at the beginning, there is no mechanical energy. At the end, there's just height energy, and there was work done by the motor. Okay? Brakes do work slowing a car as it goes down a hill, so this is the start, this is the end. Let's make this our zero of height here. So at the beginning, we have motion and we have height. At the end, we're back down to our zero of height. We're still moving, but we're moving more slowly. So I'll do a small ke here. And then work was done by the brakes. Once again, that will be a negative value. Once again, it represents an amount of thermal energy. So you could rewrite that equation and make it a conservation of energy statement for the universe. Having written a bunch of word equations, let's try a numerical problem. Here we have a cyclist who begins at rest, picks up speed, and later they're a little higher and moving. So we'll make this our zero of height. So energy at the beginning, mechanical energy at the beginning, plus the work done by non-conservative forces equals mechanical energy at the end. There's no mechanical energy at the beginning. At the end, we've got height, because they're above the reference surface down here, and we've got motion. So we've got both of those in the final state. And there was some work done by the cyclist, which will be a certain portion of the amount of food energy that was metabolized. But we just want to find this one in this case. And so we just have to calculate the potential energy, mgh, and the kinetic energy, 1/2 mv squared. So the mass is given as 50 kilos. The gravity field's 9.8 newtons on every kilogram. They end up 10 meters high. So the units end up being Newton meters, which is joules. Then they end up going at 10 meters per second. When you square meter per second, you get meters squared per second squared. A kilogram meter squared per second squared is also a joule. So here you get, let's see, 4,900, or 4,920, I guess it is. Okay, there's my problem. That wasn't 10 meters high. They just end up 8 meters high. So I just needed to fix that because the height is 8. And so now that ends up being 3920, and this ends up being 2500, both in joule units. So you get 6420 joules of useful work done by the cyclist. Now we're also asked for the amount of food energy that's used. Okay, I said we didn't need it, but actually we do. So that's the useful output over the energy input, which came from food. So rearranging, we find the food energy equals the work done by the cyclist divided by the efficiency. So that was the 6420 joules of useful work we found here, divided by 21% muscle efficiency. And if you work that out, it works out to 30,571 joules of food energy used. And the difference between those two, of course, would be the thermal energy that was created in the muscles of the cyclist. Okay, now you may wonder in the last example why we calculated work using the mechanical energy change. Why didn't we use force times displacement? Well, it's simply because we didn't know the amount of force the cyclist was exerting, nor what the displacement was. But if you have a full set of information, then calculating using either force times displacement or the energy change will give you the same answer as we're about to show here. So let's imagine we're pulling this object up a ramp at a steady speed, and let's find the work done. It's a frictionless ramp. This will be our 0 here. So the initial mechanical energy plus the work done by non-conservative forces, and I'm abbreviating that even further, is the final mechanical energy. At the beginning, there's kinetic energy at the bottom, but no height. At the end, there's kinetic energy and height energy, because it's up higher now, because it's risen, but the kinetic energy is the same. So the work done by the pulling force, because of the kinetic energy being constant, just ends up equaling the potential energy. And potential energy is mgh. The mass is 250. We'll just leave g as 9.8 g. And the height here, well, the height's not given, but we know it's a 20-meter long ramp, so that the height is just 20 times the sine of 8 degrees. Now, for easy comparison, I'm going to leave the answer in that form. Now, let's do the same problem with the force solution. So we'll start off with the force diagram. And the forces that act on the mass are gravity, straight down. Then we've also got the normal force perpendicular to the ramp. And finally, we've got the applied force from the rope, pulling it up the ramp like that. And we just want to know how much this force is, because that's the one that's actually doing the work for us. So I'm just trying to get fancy here, and I'm being unsuccessful about it. Oh yeah, so here we go. Let's just select that one and give it a color. There we go. So we want to find the work done by that force. Now for gravity, we're going to have to resolve it into its components, because gravity is partly perpendicular to the ramp in this direction, and then it's partly parallel to the ramp in this direction. Now, this component here is the same as this side of the triangle, and this angle and this angle are always the same. So we see that the gravity component here is going to be mg, and this side will be sine of 8 degrees. So you've got mg sine 8 pulling you down the ramp, mg cos 8 squeezing you onto the ramp. We've also got the normal force and then the applied force. So now let's do our force analysis. We'll call the x direction up the ramp and the y direction perpendicular. Now the sum of the x forces then, up the ramp we've got the applied force F, down the ramp we've got mg sine theta. That's going to equal the mass times the x acceleration. But because of the steady speed, the x acceleration is 0. So we find that our applied force has to equal the mg sine theta component, the slide component, down the ramp. Now work is force times displacement. So we've got the mass, the gravity constant, sine of 8 degrees, and then the length of the ramp, which is 20. Now if you compare that, mg sine 8 times 20, with the previous answer, mg 20 sine 8, you'll see that they're identical, which proves my point that if you have enough information, these two approaches can both be done and will be consistent with each other. All right. So that is more detail on the relationship between work and energy. Now it's going to be helpful for us to consider another form of potential energy. It's the energy stored in a spring. So we noticed that if you want to compress a spring, say by a distance x, then the force that you're applying is going to be given by Hooke's law. And that force is going to vary then, because obviously at the beginning there's no extension and almost no force is required to start compressing the spring. Well, because that force is varying, to find the amount of energy associated with it, or the work, we're actually going to take the average force and multiply by displacement. Now the average force will just be the average of 0 and kx, and the displacement, you've just compressed it by a distance x. So because of the averaging of the force, you come up with an expression 1/2 kx squared. So that's the work done in compressing the spring. That's going to equal the energy stored in the spring. So this is our new expression for spring PE. The energy is 1/2 kx squared. Remember, the force is given by kx, and that's Hooke's law. But the energy is 1/2 kx squared. So how do we use that? Well, we do the same sort of energy problems that we did earlier, but now we can include springs. So here you got a mass, it's moving, you've got an uncompressed spring. The mass is going to hit the spring, stop, and then we want to know how far the spring is compressed. Now, it's only going to stop for a moment, right? Because presumably the spring is going to kick it back out. But at that moment, and for every moment in between, mechanical energy will be conserved. So here we are. Initial mechanical energy. Well, it's moving, so there's kinetic energy. Let's consider the final mechanical energy. It stops, so there's no more kinetic energy. This is our zero of height. There's no gravitational energy, but there is spring energy. There's PE in the spring. Now, in this problem, because there's no friction or applied forces, there's no non-conservative work, and we say mechanical energy is actually conserved. We have the same amount of mechanical energy at the beginning and at the end. So this is what I'll call our word equation here. It just involves terms like KE and PE. We can make that into a formula equation, because kinetic energy is 1/2 mv squared. And spring energy we just saw above is 1/2 kx squared. So that's a formula equation. And we want to reduce that to a calculation. So it's 1/2 6 7.5 squared. I'm dropping the units for simplicity. We tested them above. And then the spring constant is 75. Where'd we go? Bring my pen back. 75. And then x is the unknown. And now we have reduced this to a calculation. And if you calculate to find the spring compression x, you'll see that it agrees with the answer, which is given as 2.12 meters. Okay, so that's how we can use spring energy. Now here's a problem for you to try. So what we'll get you to do is just to pause the video to try this, and then if you want, you can play the video and see the answer and compare with your work. So this is like a pinball machine. A certain amount of, you pull on it and do a certain amount of work, compressing the spring. Then you put the ball in there and you let it go and release it. You want to know, if you do 30 joules of work in process A, how far does the spring compress? And then if you put the pinball in there, at what speed is the pinball ejected? So pause the video and give that a try. Okay, so hopefully by now you've given this a try. Let's write our work energy equations. So initial mechanical energy at the beginning is just 0 because there's no motion and there's no gravitational or spring energy. At the end, we've got spring energy because we've compressed the spring by a distance x. Where did this come from? Well, you, the person, through your applied force, you did 30 joules of work, and that's going to go into the spring. So we can then make a formula equation that looks like that. We can then reduce it to a calculation by putting in the known amount of work and the given k value. And if you solve that, then you should find the given answer of 0.77. Next, so given that this is now 0.77, because we've calculated that in part A, you let it go. How fast is this going? So initial mechanical energy plus work equals final mechanical energy. At the beginning, it's at rest. It hasn't gone anywhere yet. There's no kinetic. There's just spring energy. At the end, the spring is back at 0, so there's no energy stored in it anymore, and the ball's moving, so there's ball kinetic energy. Now, you're not pulling on it anymore, so there is no non-conservative forces, no non-conservative work. Mechanical energy will be conserved here. All the energy in the spring will get converted to kinetic energy at the ball. We're assuming that the spring is very light and that it doesn't have significant kinetic energy. So now let's do a formula equation. And then let's reduce it to a calculation. And then the mass of the ball was given. How much is it? 8 kilograms. So we'll put that in there. And now we've reduced it to a calculation. You could solve for the final speed and show that it agrees. For more precision, it's mathematically astute to note above that this is just going to be 30, right? So there won't be any round off error because that 1/2 kx squared is what we identified as being the work done by the person. So it's more accurate to put 30 in for that value. All right, so now we're going to do a more difficult problem. We're going to look at a spring that's moving in the vertical plane because now we'll have to consider both types of potential energy. So this is example 9 in the book. We hang a mass on a spring and we let it come to equilibrium. So the equilibrium point will be the point where it just sits there, and that's going to be defined by a balance of forces between the elastic force in the spring and the weight. So the definition of equilibrium, let's just erase that. That implies, so here's a long implication arrow for you, balanced forces. Now, balanced forces just means that these two are the same. Or if you want, the sum of the y forces, which is an upward spring and a downwards weight, will be 0 because it's at equilibrium, it's at rest. So the spring force is kx, it's going to equal mg, so we can find the compression of the spring and reducing it to a calculation, and then actually solving that. Okay, so that works out to 13.1 centimeters. So from where the spring is at rest to equilibrium is 13.1 centimeters. So that's sort of the first part of the problem. Now in the second part of the problem, we're going to pull the spring down another 10 centimeters. We're going to let it go, so it's going to start at rest. And then we want to know when it gets back to this point, how quickly is it going to be moving? So this mass, if you release it down here, is going to oscillate. It's going to go up and down like that. And so when it reaches the equilibrium point, now it will be moving. All right, so how will we approach this? Well, we're going to use the work energy theorem. So initial energy at the release point plus work by non-conservative forces equals final energy when it's back at equilibrium. So here we're going to have kinetic energy, gravitational energy, spring energy. All three forms of mechanical energy can be present in this problem. Fortunately, this is 0 because the only forces are gravity and elasticity, and they're conservative forces. So mechanical energy will be conserved. In this picture here, there will be kinetic energy, there will be gravitational energy, and spring energy. Now let's think for a bit about our variable assignments. Here at the release point, it's at rest. So there's going to be no kinetic energy. For gravitational energy, why don't we make this lowest point here, this lowest point, our 0 of height? That's terrible. Let's do that again. So we want this lowest point to be our 0 of height. I'll just use the line feature and make that a lot better. There we go. Oh, that's so much nicer. All right, now the pen feature, h equals 0. Okay, and this was 10 centimeters. Okay, so all that means is that at this point, there's no height either, because we're saying that's our 0. Now for spring energy, we care about how far the spring's been stretched. Well, remember, starting up here, we stretched 13.1 centimeters to reach equilibrium, and now another 10 centimeters, so we're stretched 23.1 centimeters at the release point. Coming back to equilibrium, it's moving, so that's our unknown. We definitely have height because we're above the 0. We're actually 10 centimeters above the 0. And at this point, we definitely have spring compression. Remember that the spring compression is 0 up here, so we're 13.1 centimeters of extension at that point. So now we can set up our formula equation and substitute in and reduce this to a calculation. So k is 750. The initial x is 0.231 in meter units. The mass of the object is 10. I'll just call the unknown v. So this is 10 g. The final height is 0.1. K is 750, and this is 0.131 meters squared. So that's reduced to a calculation. If you do the calculation, you should get 0.866 meters per second is the speed when it returns back to equilibrium.